It's time for some honors geometry, chapter 9 review here. Good morning, afternoon, or evening. I don't know what time you're watching this, but this is morning for me. Let's get after it here. Chapter 9a review. We've got ourselves a triangle here. We've got ourselves a right angle as well. Awesome. Measure of angle ABC is 120 degrees. BD is bisecting that angle. Oh, right away, you know what I'm going to do? That's 60 and 60, isn't it? Those guys are congruent. Beautiful. AB is 7. And if I've got BD as perpendicular to AC, I know from previous problems that this is going to be an isosceles triangle with that perpendicular bisector happening right there. That is awesome. Okay, so we got a lot of symmetry going on here. These guys are congruent. These guys are congruent. Oh, this is beautiful. This is beautiful. So let's isolate some things here. I want to find AC and I want to find BD. What I've got here is a 30, 60, 90 triangle. Two of them actually, 30 and 30. So I'm going to work with one of them here, okay? Now this side that I have, AB, is my 2x side. So if I cut that in half, I get the side that is across from the 30. So I get BD is 7 over 2. Look at that. BD equals 7 over 2. That's one of my answers already. That's a weird looking 2. I'm gonna, there we go. That's a little better. That's a little better. So now that I have BD, I can't get AC, but I could get AD, right? AD is going to be, let me flex some teacher brackets there. AD is going to be 7 over 2 root 3. Okay, cool. Or we could say 7 root 3 over 2 if you prefer that version. Either one of them is fine. Now, if I want the whole thing, we already know that they're congruent, right? We got all this wonderful symmetry going on. We got a isosceles triangle. We got that. Oh, this is great. I can double that. So if I take 2 times 7 root 3 over 2, boom, boom, I get 7 root 3 for AC. So AC equals 7 square root 3. Bingo, bango. First one in the books. That's 1 of 10. Okay, we are 10% done here. Let's keep moving and grooving. All right. Problema numero dos. All right, so we want to find the sum of x and y. I've got x over here is that hypotenuse, it looks like. We got y as one of the sides of a right triangle. All right, so these right angles, keep in mind that if that's a right angle there, this is a right angle here, this is a right angle. We got 4 right triangles we're dealing with, right? Well, right away I see y. That's a 6, 8, 10 triangle. It's a 3, 4, 5 that has been doubled. I know my triples, they won't be tripping me up. Oh, okay. So if that's 8, and I've got congruent markings here, this is also 10 over here, which makes this also a 6, 8, 10 triangle. Holy guacamole, I'm cruising. And I've got another right triangle with an 8 and a 17. That's an 8, 15, 17 triangle. That's beautiful. That's fantastic. Where do we go from here? You know what I forgot to do here? Do you know what I forgot to mark when I made up this problem? These were supposed to be congruent here and here. My apologies. I do apologize there. I meant to put those congruent markings. Now that we have them, we know that this guy right here is 15 as well. Okay? And if looks like an isosceles right triangle. Remember that terminology there. Isosceles right triangle. 2 congruent sides, it's a right triangle, an isosceles right triangle, which is also going to end up being a 45, 45, 90 triangle, because if those are congruent, these 2 angles are congruent, which makes them both 45. That is an isosceles right triangle. I don't know how many times I've said that. Maybe it'll come up on your test. I don't know. Maybe I'm just crazy. All right. So if it's a 45, 45, 90 triangle, given from the whole isosceles right triangle thing, I know that the hypotenuse there is just root 2 times bigger than the leg. So this would end up being 15 square root 2. Wonderful. Fantastic. Awesome. So what's the sum of x and y? That would just be 8 plus 15 root 2. And you might be like, well, that's stupid. I can't even put them together. Too bad. I don't care. That's the answer for that one. That's the exact. If we asked for a decimal approximation, you would just type that into your calculator, round accordingly. Okay? Cool. Fantastic, wonderful. I'm going to keep saying fantastic and wonderful here. Let's go on to problem number 3 here. We are 20% of the way done. We're on the third problem. one diagonal of a rhombus, if you forgot how to pronounce it, it was rhombus. I'm just kidding. It's rhombus. The H is silent, okay? Don't say rhombus. People, math teachers might make fun of you. I'm just kidding. All right, rhombus is 30. The diagonal of a rhombus is 30. The perimeter is 68. Find the measure of the other diagonal. Now watch this. I'm about to flex some technology on you. You ready for this? I hit ink to shape. Let's see if it works. Make myself a dope rhombus. It's kind of more parallelogrammy. So I'm going to go again. See if I can get it better. Still kind of parallelogrammy. Whatever, I don't care. All right, 2 tries is all I give myself. So I'm going to draw on some diagonals here with my dope ruler. Let's see if we can get, that's almost, and that's close enough. Boom. And then I'll get the other one here. So I'm just drawing on my diagonals. Now, what do we remember about our diagonals of a rhombus there? Well, my diagonals of a rhombus are not only perpendicular, but they also bisect each other. Now, they might not look that perpendicular here because it was a little more parallelogrammy than rhombusy. But in any event, they are perpendicular. They bisect each other. I like that. What do we know about all the sides of a rhombus? They're congruent, right? So if my perimeter is 68, I can divide that by 4, and I can get 17 for all my sides. Well, that's cool. Now, 30 is the diagonal of one of them, which means if they're bisecting each other, half and half would be 15 and 15. Now, I didn't have to choose that diagonal. I could have done the other ones, but I decided to do that one because I know the answer. All right, and it will look more aesthetically pleasing if I do it that way. So I have 15, I have 17. Oh my goodness, this is another triple. 8, 15, 17. And if these are both 8, then the other diagonal measure is 16. Whoop, whoop, whoop. My goodness. Triples again? How many times have we used triples already and we're only on the 3rd problem? Perhaps you should know them. All right, if you don't remember them, we have 3, 4, 5. I don't want to go to 8 yet. 5, 12, 13, 8, 15, 17, and 7, 24, 25. You know what's funnier than 24? 25. Do you remember that reference? Okay. So, awesome, fantastic, wonderful. 4 of those triples, we can double them, we can triple them, we can cut them in half, we can multiply them by 10, we can multiply them by root 7, we can divide them by 82. You're not going to really see that. Most of the time, you're going to see them either doubled, tripled, or quadrupled. Mostly doubled and tripled. Okay? Cool. Awesome. A rough door opening is 31 inches by 81 inches. To make sure it is a rectangular opening, what length should the diagonal be? Well, if I frame out a door, let's do this here because I'm getting a little application-y with it, right? I'm getting a little application-y. So if I frame out a door, here's the ground or the floor. There's my rough opening. Okay, so we're saying it's 31 inches by 81 inches. Now, oftentimes, so like a door is usually like 30 inches by 80 inches, and they'll frame it out maybe like ½ inch to an inch bigger. That way they can fit it in there, and they do what's called shim it into place and adjust because the framing is not always perfect. But if we want to get it pretty much perfect, we're asking what should this measure be right here if we're going to have a rectangle which is going to have 4 right angles, because we want right angles, right? We don't want a parallelogram door opening. But when I have my opposite sides, 81 inches and 31 inches, all I'm guaranteed is that it's a parallelogram. We know that from chapter 5. Opposite sides are congruent. To be a rectangle, my diagonals would have to be congruent. Well, what would the measure of those diagonals be? Let's find out one of them. I'm going to pop up my calculator. But before we do that, let's actually write out something. I've got a right triangle, and I've got 2 known sides. How about a little Pythagorean Theorem? So this one's not a triple. I know, weird, right? If I call this, let's call that x. So x squared. I'm going to have to do, use the calculator on this one. This one's a little messy, more of like an application-y type of problem, hence what I'm doing here. So let's plug that into our TI-84. So we got 31 squared plus 81 squared, enter. 7,522. But that's x squared, right? So I'm going to have to square root that. Or here's what the cool people do. You ready for this? If you want to be a cool person like me, all right, I'm going to raise that to the 0.5. Raising it to the 1/2 or raising it to the 0.5 is equivalent to square rooting it. You may remember that from Algebra 1 honors. I don't know. But if that freaks you out, if you're like, dude, I cannot handle that, you can just do square root of 700 or 7,522. All right? That's fine as well. And just to show you that they are equivalent. I'm not a liar. I wouldn't lie to you, okay? So we're looking at 86.73 when we round it. 86.73 inches. So if I was hanging out on the job site and I was framed at the store, I would know that they should be about 86 3/4 inches. I'm gonna be feeling pretty good about it. But that would be our answer on this test here. Is we're gonna keep things as exact as possible. Whew. That's good stuff there. So both diagonals should measure that. You don't even actually have to do any math. You can just measure them and you're like, oh, it's 86 and about 3/4. Let me check the other one, 86 and about 3/4. We got this thing squared up pretty darn good. Boom, we can put that door in place and we'll level it out from there. All right. Awesome sauce. So next one. Not even geometry. Just solve for x. 2x squared minus x equals 10. Oh my goodness. Is that a lead coefficient? Is it not even set equal to 0? What are you doing to us, Mr. Allen? Oh, I know, right? Boom. Already set equal to 0. Now I got a lead coefficient factor. All right. There's a couple methods of doing this. Most of you end up doing rainbow method, where we're going to take 2 times negative 10. That's negative 20. And I want to add to negative 1. Okay? Well, what numbers would do that? Negative 5 and positive 4 would do that. And you might be like, oh, I'll just do x minus 5, x plus 4. And then I'd be like, you're wrong. All right? We can't do that with a lead coefficient. Takes a little bit more. All right? So I'm going to have 2x squared minus 5x plus 4x minus 10 equals 0. Now, why does that work? How are we able to change this problem? Negative 5x and positive 4x add up to negative x, right? So I haven't really changed anything. I've just broken it apart a little bit. Now, I'm about to throw some parentheses around the first two and the last two, okay? I'm going to pull out a GCF time. First one, I've only got x that I can pull out, and I'm left with 2x minus 5. The second one, though, I can pull out a 2, and I'm left with 2x minus 5. Oh my goodness, we got 2 of the same factors. Those are actually GCFs in themselves of these two now awkward looking terms here. So I can pull out a 2x minus 5, and then the leftovers are going to be x plus 2. That equals 0. This is now factored. It's time to solve. So if I set 2x minus 5 equal to 0 and x plus 2 equal to 0, I will get x equals 5 over 2. And x equals negative 2. Now, since we're not dealing with an application situation, these are just our two answers. That's it. Sometimes we'll ask you for the sum of the two solutions, the product of the two solutions, the difference of the two solutions. What is the largest solution? Okay. What is the smallest numerical value for the solutions? Whatever. We can ask for all sorts of different things. SAT loves to do that, where you get one answer here, even though it's a 2-answer type of problem. We ask for one of the answers in a creative way. So you might see that on a test, especially when we're dealing with like Google Forms and things like that. We want one answer, or multiple choice type problems. Woo! Woo! Good stuff. All right. We are halfway done, folks, except for one of them is a 3-part problem. Some crazy. I was told my 9.5 video distance formula just wasn't enthusiastic enough. And it was like I was not that into it. So I'm trying to, got to make sure that I'm happy here. I'm getting enthusiastic, pumped about the math. I'm going to get a drink. All right. Halftime's over. Let's go for this. Let's do it. Woo! Triangle ABC is a right triangle with AB congruent to BC. If AC equals 20, find the area and perimeter of the triangle. Okay. So it's a right triangle. AB is congruent to BC. This is a right triangle with 2 congruent sides. I feel like I said something like 80 million times earlier about a right triangle. That was isosceles. Isosceles means 2 congruent sides. I got 2 congruent sides and I got a right triangle. This is an isosceles right triangle. So I'm going to draw it as such, like a 45, 45, 90 triangle. Now it says AB and BC are congruent. AC is 20. So this is going to be A, B, C. And how did I know that? Well, let's see here. AC is 20, AB and BC are the congruent ones. AB, BC are the congruent ones. The only ones that are going to be congruent are the ones that stem from the right angle, because the hypotenuse isn't going to be congruent to one of the sides because it's the longest side. So how can it be congruent to another side if it's the longest? Right? So since AB and BC are congruent, those are my two legs. That's how I drew this, or I knew how to draw it. Knew how to draw the whatever. All right, AC is 20. Now I want to find the area and the perimeter. Okay, so we said this is a 45, 45, 90 triangle. An isosceles right triangle is a 45, 45, 90 triangle. So I need to divide 20 by root 2 to get back to one of the legs. So 20 divided by root 2. I'm going to rationalize that. And I get 20 root 2 over 2. And some of you might be like, why did you just simplify that right off the bat? I'm trying to show some steps. Okay? So we get 10 root 2 and 10 root 2 for my two sides. All right. So now we want area and perimeter. Okay? I'm going to switch colors here so it's not so monotonous. We'll go purple. So area, that's 1/2 base, which is 10 root 2, times height, which is 10 root 2. The one thing with finding the area of a triangle, remember the two dimensions you're using have to be perpendicular to each other. Those are the two that are perpendicular. That's why I'm not using the 20. All right. So I got 10 times 10 is 100. And then root 2 times root 2 is root 4, which is 2. So in an effort to not really do a whole lot of calculator stuff, I'd have 100 times 2, but the half and the 2 go away, and I'm left with just 100 units squared. You know, we don't have any units here, so I would put 100 in for my Google form. No units if we're doing Google Forms. All right. As this is created right now during, remote hybrid funness, that's why I'm referencing the Google Forms. In the future, I want to get away from that. I can't wait, right? I can't wait for the future. But now it's getting better. All right. So you got 100 for the area. Lovely, fantastic, wonderful. Perimeter. What do I do to get perimeter? Perimeter, add all the sides. So let's do that. If I add all the sides, I'm going to go green now. Green's my favorite color. If I add all the sides here, it would be, so let me write perimeter. It'd be 10 root 2 plus 10 root 2 plus 20. So I got, 20 root 2 plus 20. There's my perimeter, or 20 plus 20 root 2. I'd leave those separate. They're not like terms. They stay separate. I know it's like, wanted one single answer. Sorry, can't have it. All right, 60% of the way done. That's some quick math right there. I really hope that it was 10 problems that I made up. Now I'm second guessing myself. I think it was 10. Number 7. What is the altitude of an equilateral triangle if the perimeter is 24 feet? Well, that sounds fun. Sounds exciting. An altitude is the same thing as a height, right? Those are interchangeable terms. So altitude, height, the perimeter of the equilateral triangle is 24. Equilateral triangle has all congruent sides, so each side is 8. Right, yes, I do stop to take a breath sometimes, okay? So I've got 8, 8, 8. Now, the altitude of an equilateral triangle is going to come down like that. It's going to be perpendicular because it's an altitude. It's a height, right? Now, the wonderful thing about an equilateral triangle is much like an isosceles, when you drop down that altitude from there, it's going to split that side up, right? If it's an isosceles triangle, it's going to split the side across from the vertex angle where the two congruent sides meet. It's going to split that opposite side in half perfectly, right? It's going to bisect it. Same thing with equilateral. So these are going to be both 4 and 4, with this whole side being 8. Woo! Teacher brackets. Cool. So I got 4, I've got 8. Now I could do one of two things. I'm going to show you both ways. I could do Pythagorean Theorem, where it would be 4 squared plus x squared equals 8 squared. So I'd get 16, 64, x squared, so I get x squared equals 48 square root, and then I'm going to simplify that down. It's 16 and 3. Square root of 16 is 4. 3 stays in, 4 root 3. Or, had you known all the angles of an equilateral triangle are 60, which would leave 30 for this one, it's a 30, 60, 90 triangle. I've got the one across from the 30. That's just 4 root 3. Then I multiply that short side, the one across from the 30, by root 3 to get the one across from the 60. Look at that. That was actually way faster than Pythagorean Theorem. Only because I had the 30, 60, 90, if I noticed that. But I had two sides of a right triangle, so Pythagorean theorem would have worked as well. It's nice to have multiple ways to do a problem, especially if you like don't remember one of them. You got a 50-50 shot of remembering it then, right? I don't know if it works that way. All right, 70% of the way down. On to number 8. Here's our three-parter. I need a drink before this. That's some good cold water right there, right? That's not all coffee. You might think that's all coffee. I already had my coffee. 2 cups, American flag cup and travel mug. Woo! All right. Let's see here. So these are 3 individual problems, A, B, and C, okay? They're going to be done independent of one another. We're going to do one of them. I'm going to erase. Then we're going to do another one. Okay. So the first one I'm going to do is going to be in green. We got AC is 12. Teacher brackets. I got AD is 8. Teacher brackets. And then we got BD is what we want. Okay. Interesting. I'll call that X, right? This is altitude on hypotenuse. I have a right triangle with an altitude dropping down to that hypotenuse, right? It's an altitude because it's perpendicular. Perpendicular gives you altitude. Altitude gives you perpendicular, right? So this is altitude on hypotenuse. I can get DC by subtracting. That makes this guy, teacher brackets, 4. And if I remember my formulas, that altitude, x squared plus, sorry, not plus. I don't know why I'm saying that. X squared is equal to the product of the 2 that it splits. So AD, which is 8, times DC, which is 4. X squared equals 32. Square root both. And I get, let's see here. This would break out to 16 and 2. Now, if you're like, I got to go prime factors, keep going and circle your pairs. But I like to do this. 16 is a perfect square, so I get x is equal to 4 root 2. Square root of 16 is 4. 2 stays in. Boom. First one's done. Awesome. Now, if you need to, feel free to pause at this point to see the whole thing, because I'm about to pause my video, erase the green on the diagram, and then I'm going to do part B. All right, part B. And actually, let me go with, this is A right here. Part B, I'm going to go with, orange. How about orange? Orange sounds fun. Okay, so for part B, when I label my diagram here, I got BC is 3 root 2. Who puts a root 2 in a length? Weirdos. There we go. DC is 2. And then find AD. So I want that whole length right there. Okay, my altitude and hypotenuse theorem formulas, okay, another one of them. I'm going to take that BC, which is 3 root 2. That one squared is equal to the close side, the DC side 2, times the entire thing, which would be x plus 2. Okay? Now, since I'm trying to find AD, I called AD X. Had I been looking for AC, I'd call that X. But since AD is what I'm looking for, I call it X, and then I'm left with that X plus 2 in there rather than some other variable by itself. This way, when I solve, I know that X is my answer, okay? It doesn't always allow you to do that, but whenever we can, I like to assign the variable to the side that I'm solving for so I don't forget to finish the problem. I've done that before, forgetting to finish the problem. I did that the first time I took the final in honors geometry to test things, and I ended up getting like an 80-something% because I just didn't finish the problems as I was like distracting myself with emails and things like that. So anytime I can set a variable equal or set the variable as my answer, I'm going to do that. And that's what I did here. I'm going to move on. Okay, I think I've hammered that down. So 3 squared is 9, and root 2 squared is 2. The square root and the squared cancel. So I'm left with 9 times 2, and then I get 2x plus 4 when I distribute that 2. Common mistake is to square, or just to do the square root and the squared, cancel each other, and do 3 times 2, which is 6. And then everything goes haywire after that. You don't want to do that. All right. Don't forget that, yeah, that goes to both parts. It distributes in. There's no addition in there, so you can distribute the exponent, and then this got distributed. Okay. So 18 equals 2x plus 4. Subtract 4, I get 14 equals 2x. So x equals 7. There is my answer. That's AD. AD is 7. If I asked for AC, it'd be 9. Wonderful. Fantastic. All right. On to part C, We'll do part C in, how about, ooh, this one looks fun. We'll do that. All right, part C. And I'm going to go ahead and erase these guys here, and then we'll relabel the diagram. So AB is 2 root 5, another square root in our setup. Ugh. And I got DC as 1, all the way the heck over there. Find AC. I want the entire thing. What? Now here is where things get tricky. If I make AC my X, when I set this up, AC, that whole side, is a part of that formula, but so is AD. So now I'm dealing with having to label AD as something. So my suggestion here is just to say AD is my X, okay? AD is my X, and now when I set this up, I've got 2 root 5 squared is equal to X, that closed part, times the whole thing, okay? So this is a situation where I would suggest setting it up this way. AC is not my X right now. I'm going to have to plug back in and find my final solution. Okay, otherwise I have to do like set the whole thing X and then do like X minus 1. People might mess that up. So this is where students are most successful in this style setup. So I've got 2 squared is 4 times the square root of 5 squared, which is 5. So that's 20 over there. And then I'm going to have X squared plus X. Oh boy. Of course, we've got factoring over here. So let me zoom in on this one over here. So we've got 0 equals X squared plus X minus 20. I'm going to factor. I know you're probably freaked out like, whoa, why is the 0 on the left, Mr. Allen? You can't do that. Yes, you can. So what multiplies to negative 20 and adds to 1? Well, that would be positive 5 and negative 4. So I'm going to get X equals negative 5 and X equals positive 4. Now, if I back out, negative 5, that would be my length, right? Because X is a length of a segment, AD. So there's no way that's going to be the case. But 4 would work. However, pump the brakes. 4 works, but 4 is not our answer. AC is equal to, if this is 4, AC is equal to 5 for my final answer. So make sure to double check that you have the correct answer. Whew. This has turned out to be a beefy review here, right? You know, this has got some stuff going on. I like it. 2 more problems. I apologize for the length, but hey, got that test coming up. Video review. This is pretty dope. 3D time. All right, we're in the last section here. A little 3-dimensional action here. I'm pretty psyched for it. I love me some 3D. I decided to just copy and paste the diagram here. Not that I can't draw these. I can draw these very well, but with the 3D shadowing, I felt like digitally, sometimes it's a little tricky with this pen. So height of a square pyramid is 16. Okay, so if I pop the height in here, I'm going to go like that, and I'm going to go down to the center there. So that will be, boom, right there. Okay, and then I'm going to also draw into the midpoint of that side roughly. Boom. And then I'm also going to draw in our slant height. There we go. Lovely. Okay. That's all the important stuff in that square pyramid. So we get like these triangles within, okay, with triangles within the 3-dimensional diagram. Okay. So the height of that square pyramid is 16 meters. The area of the square base is 576. Okay, hold up. Area of the base is 576. What's the formula for the area of a square? And I know we haven't dealt a ton with area, but area of a square you should know, okay? Side squared, right? So X squared is equal to 576 with these sides being X, right? So if I square root, because both the sides have to be the same for a square, if I square root this, I'd get X equals 24. All right. So 24 meters. So that's one of the sides of that. So I'm gonna jot that down, 24 meters right there. All righty, find the slant height and the diagonal of the square base. So 2 separate things. Slant height, we'll call that Y. And then the diagonal of the base, I'm gonna pop that ruler back in. The diagonal of the base is gonna be, I'll actually draw it going through this way. Whoop, there we go. That's my diagonal of the base. Okay, we'll call that Z. Cool. So So let's deal with the slant height first. 24 meters for one of the sides of the square base. So guess what? Teacher brackets. Just that piece is. That right there is going to be 12 meters. It's a terrible M. That's still terrible. Let's try one more time. Third time's a charm. That's better. All right, so that's 12 meters. And guess what? The height is perpendicular to that center of the base, so that's a right angle. That's a right triangle. So what I'll often do is I will then redraw this 12, right angle, 16. This is a, do you see it? Do you see it? Do you see it? Divide those all by 4. I get 4 and I get 3. This is a 3, 4, 5 triangle that has been multiplied by 4. 5 times 4 is 20. So my slant height is 20 meters. 3, 4, 5 triangle for the win. All right. Next one, the diagonal, Z. We did say this was a square base, right? But it looks kind of messed up when it's in 3D, right? Because we're trying to get some dimension to it. So if I redraw this square base just like this with 24 and 24, and I draw that diagonal in, this is a right angle here because it's a square. Do you know what we know about diagonals of a square? They bisect the angles. And if these angles are right angles, then bisecting that gives me 45 and 45. Not to mention, we got a right triangle here when we cut it in half with two sides that are congruent. That's isosceles. That's an isosceles right triangle. That's a 45, 45, 90 triangle. How do I find the hypotenuse of a 45, 45, 90 triangle? If I know the leg, I take that leg, I'm going to multiply it by root 2. So I get 24 root 2. So the diagonal of the square base, diag of square base equals 24 root 2 meters. Woo! Play that back if you need to, because I did go a little bit fast, right? But I was excited. All right, awesome. Isosceles right triangle is a 45, 45, 90 triangle. Maybe that'll be important one day. I don't know. All righty. Last one. A rectangular prism has dimensions 3 feet by 4 feet by 12 feet. Find the length of the diagonal that runs through the solid. Perhaps I should draw a rectangular prism. And I know I just grabbed one before, but now I feel like, I've been challenged here. Okay. I'm going to go with green, favorite color, for this last problem here. All right. Are we ready? And I'm going to draw it like this. Boom. Rectangular face. Get that 3D going. You know what? I don't like the rounded corner there. Last time. That's a little better. Boom. 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 Same angle. Drop it down. Now, here comes the challenging part. Okay. Mic drop. All righty. We got ourselves a rectangular prism. Now, it says the dimensions are 3 by 4 by 12. And you might be like, well, how do I know where to put them? It actually does not matter, but I'm going to set it up how I want in an advantageous way. I'm going to say this is 3 feet, this is 4 feet, and this is 12 feet. The reason why I'm doing that is when I look at that base, and I've got, with a rectangle, I've got all right angles all over the place, right? It's a rectangular prism, so everything's a right angle that we see here. So that means that this, and I'm going to switch colors here for drawing on it, this is a right angle there, even though it doesn't really look it, right? That's a right angle. So that means that this is a right triangle right here. Okay? And if that's a 3 and a 4, that means that my diagonal is a 5 foot. 3, 4, 5 triangle. Did the triples come back again? My goodness. Okay. So I've got that dimension. Now, let's see what else this wonderful rectangular prism gives us. If I were to draw in my diagonal that runs through the solid, we're talking from corner to corner, okay? If you got a tissue box handy, take that thing. I wonder if I got, nope, I don't have one. All right, hold on. All right, so if we're talking about a rectangular prism here, we're talking about the diagonal that runs through the solid, I want you to envision a rectangular prism. I happen to have one handy right here. I got a microwave, okay? We got a microwave. So we're talking about from like this back corner here all the way to the front right here, okay? Let me see if I can back up my laptop a little more for you to see this, okay? So we're talking from this front corner here all the way to where my hand is there. See how I'm holding this thing? Okay? We're running through the microwave. Okay? From the back corner all the way to the top right here. Okay. We'll put this microwave back now. All right, I just found out that I can go full screen with this thing. So now let me do this again because I feel like that might have been a little hard to see. So I got my microwave, right? So where I'm holding my hand right here to the top right here. So see how I'm going through the microwave with my diagonal. Okay, that's the diagonal through the rectangular prism. All right? I think we got ourselves a visual. I'm going to get back to the math. So that's kind of fun. I can make this thing really big. Hello. All right, let's go back down to small. That was fun. I'm out of breath. Don't worry, the microwave's fine. Microwave's fine. Just kind of the plate moving around. All right. So, did you know that Mr. Philpott put tortillas directly on the microwave plate? Who does that, right? Put down a napkin or a plate, right? If you go directly on the microwave plate, I can't trust you with anything. Okay. So we've got our diagonal through the salad, right? Through the salad. That's the one we're looking at. So we got 5, we got 12. Remember how I said that everything is a right angle here? Boom. That's another right triangle of 5, 12. 13 feet. There's my diagonal. Boom. All about the triangles. When we're dealing with three-dimensional figures, draw your triangles. Draw them off to the side if you need to because they look kind of jacked up in 3D, right? They don't look like right triangles, so redraw them if you need. There we go. All right, you guys have a wonderful day. America, freedom, rock and roll, Costco, Riverdog Jenny on the ground. See ya.